Good afternoon, everybody. So my name is Oleksii Starov. I'm a PhD student at Stony Brook University. And today I would like to present our paper, XHound, Quantifying the Fingerprintability of Browser Extensions. This is a joint work with my advisor, Professor Nick Nikiforakis. The popularity of browser extensions has increased a lot, and today we have thousands of popular browser extensions in Chrome store or Firefox store. And many of them have actually millions of users, and here we see examples of such extensions. So like those extensions block ads, manage passwords, add shopping buttons or other controls, or actually just change the appearance of websites. At the same time, extensions are considered to be more private. Previously, researchers showed that older browser plugins were one of the most powerful features for fingerprinting, and we have several studies like that. Nowadays, plugins are fading away because of security and performance issues. And in comparison to plugins, there is no API for a web script on a web page to enumerate browser extensions installed in a browser. Though are extensions really that undetectable? Let's consider the following example. So this is a simple YouTube video page without any extension being present in the browser. And this is the same web page with magic actions for YouTube extension. Let me try one more time. And everybody can notice that the page actually is different. We see these additional controls under the video, and we see actually that one ad was removed actually from the actual video. And those web changes are changes to the DOM tree of a web page that can be easily detected by any script running on this page. It appears that many browser extensions actually introduce similar visible side effects. And actually, all these extensions, popular extensions that we saw on the first slide, they're all detectable via their visible side effects, whether they add some additional content or block it. For example, some block malicious scripts or ads. Obviously, this has privacy and security implications. First of all, if there is a known vulnerability and exploit in one of detectable extensions, attackers have an easy way to discover victim browsers. And here we can consider, like, for example, example of password manager like LastPass, compromising of which can have severe security consequences. Secondly, exposing sensitive browser extensions can be by itself privacy intrusive. For example, we can consider such cases as extensions for encrypted communication like Mailvelope, extensions for VPN services, shopping discount extensions that actually may reveal your income level, or political add-ons that actually may reveal your political views. Moreover, extensions can be used as a new fingerprinting feature. And the discriminating power of this feature, it depends on the fact whether different users tend to have different sets of detectable browser extensions. And this is the goal of our paper, basically of our study, to measure this fingerprinting power of browser extensions. For that, we answer the following questions. First of all, how many extensions out there are actually detectable via their on-page side effects? What on-page modifications they introduce? How fingerprintable are extension profiles of real users? And finally, we also implement proof of the concept fingerprinting script that can be used like by trackers, for example. We also consider like two threat models. First of all, if any arbitrary website wants to fingerprint extensions of users, they can fingerprint only those extensions that introduce visible side effects regardless of the URL and domain. And here we see example of such extension, LastPass again. So basically, like it's enough for a web page to have a web form with password field, so that LastPass will inject this three-dot button. And actually, we see on this slide under the hood how it looks like in the DOM tree of a web page, how the changes look like, and also can be detected. Another threat model is a popular URL, popular website that wants to fingerprint user. For example, like we can consider here save-to-pocket extensions that introduce this save-to-pocket button on tweets on a Twitter website. So basically, like Twitter can fingerprint also these extensions. In general, we consider here that popular websites have more extensions to fingerprint. And again, we see how it looks like in the DOM tree. To test extensions on fingerprintability, we developed a special framework, XHound, or extension Hound. That gives us ability, first of all, to prepare extension for testing, and then to execute tests with Selenium's Chrome driver. Basically, we take each extension, each browser with extension to different popular URLs and also our custom URL. But instead of visiting real websites, we pretend to visit those URLs, and instead we visit our specially crafted honey pages. As a result of each test execution, we save the final state of the DOM tree of a web page. And as a final step of the analysis, we basically compare these DOM dumps with the DOM nominal. And by doing that, we can extract basically the modifications that were caused by extension. Our honey pages have prepared static content, and also they create dynamic content on the fly. The aim of both is to trigger as much as possible of benign and legitimate functionality of extensions. Under dynamic content, I mean basically our on-the-fly DOM JavaScript library that basically intercepts all DOM queries from extension and creates on-the-fly the queried hierarchies of the DOM. So basically, we intercept get elements by class name or another queries like query selector. We also support multi-step queries. After running XHound over the top 10,000 popular Google Chrome extensions, we've arrived at the following results. First of all, more than 9.2% of extensions introduce detectable changes on any arbitrary URL. So basically, any web page can fingerprint those extensions. And more than 16.6% introduce detectable changes on at least one popular URL. And here we see basically the fraction of detectable extensions versus different ranges of a rank. And we see here that more popular extensions with higher rank have like a larger fraction of detectable extensions, though the tail is also pretty stable. The next question was what type of DOM modification extensions actually introduce. And here we have like two important points. First of all, out of all the detectable extensions discovered with XHound, more than 86% have at least one totally unique on-page side effect. That basically means that they can be uniquely discovered on web pages. The second fact is that these DOM side effects are actually rather stable because we repeated our experiment after 4 months and also arrived at the similar results. Next, on the table, we can see here that the most popular modification is addition of some DOM elements, some additional content. And the second one is changing attributes of some particular DOM elements. And actually, this like second type of modifications was discovered greatly because of the use of our on-the-fly DOM library. We also analyzed detectable extensions per category. Here we see that basically like shopping extensions are more fingerprintable, also on any arbitrary URL, and even more extensions on some popular URLs, because like some shopping extensions, they are tailored to some particular online store. We also see social and communication extensions very detectable on some particular websites, particular social networks. And such extensions as universal, as like belonging to such categories as productivity, accessibility, photos, they are likely to be fingerprintable on any arbitrary URL. We also tested top 1,000 Firefox extensions. We considered here two latest technologies for Firefox add-ons, naming web extensions and add-on SDK. And we also like got pretty similar fractions. So basically 16% of extensions are fingerprintable on at least one URL, and over 7.3 extensions on any arbitrary domain. And we see as examples Firefox versions of fingerprintable Chrome extensions like Ghostery or Grammarly, and also like specific cases for Firefox like ZenMate VPN. In the second part of our study, we surveyed real users to collect extension sets in their browsers. For that, we developed a special browser survey extension that can extract active extensions present in the browser. And in addition, we also collect the sizes of browsing histories to identify frequent Google Chrome users. So basically, we analyzed 854 browsers of unique participants. Those are Mechanical Turk users, students from Stony Brook University, and also friends and colleagues. Overall, they had 941 unique browser extensions. And out of those, 174 were fingerprintable on at least one URL, and 93 on any arbitrary website. OK, to analyze how those users can be fingerprintable, can be fingerprinted using extensions, we basically analyze the picture in terms of anonymity set sizes. And here we see results for different surveyed audiences separately, like for students, US mechanical Turk workers, non-US, friends and colleagues all together, or frequent Chrome users. And in either case, we see that basically from 14% to 24% of users belong to anonymity set of size 1. That basically means that they have extension-based fingerprint unique, and they can be totally uniquely identified. Similar fraction of users also in each groups share their extension-based fingerprint with 2 or up to 20 other users, and even more from 21 to 50 other users. Let's consider how it looks like in terms of entropy. On this slide, you can see like normalized entropy and actual entropy of what we got with extension-based fingerprinting. And we also compare our results with uniquemachines.org with results that they reported in the recent NDSS 2017 paper. The surveyed audiences sizes are pretty close, and that's why like we leverage that to compare. So first of all, we see that in terms of normalized entropy for some audiences that we surveyed, basically extensions can provide even better entropy, perform much better for fingerprinting even than list of plugins. And in terms of actual entropy, we see that also like extensions give totally non-trivial entropy here as well. Let's see now what actually XHound extracts, what modifications. First of all, XHound gives us ability to extract triggering content to trigger modifications that extension introduce. And it can be like such simple cases of like very small parts of the DOM. Or it can be like larger hierarchies also created on the fly with XHound. And basically this particular example serves if Google Calendar extension finds such hierarchy, it injects this link and image highlighted with blue. In order to develop the final fingerprinting script, we also need to have some kind of detection logic. And here we see how it looks like. So basically, it's straightforward, one if statement for each particular extension. And inside each if statement, we can have like 1 or maybe 2 if you want to have a cross-check queries to the DOM tree of the page. So this runs very fast, like a couple of milliseconds. And in terms of performance, that's why we measured the only bottleneck that exists. It's extension load times. So basically, it means how much time is it needed, like for all extensions being active in the browser, to reveal themselves, to introduce visible modification after web page load. Of course, like if you have many extensions in the browser, the assumption is that they introduce modifications slower. And here we analyze the situation for up to 20 extensions simultaneously being present in the user's browsers. So according to our results, usually users have on average 5 extensions only. But in either case, we see that it's enough to be like less than a second after web page load, so all the modifications being introduced and detected by XHound. We also have a video demo that we used for this performance evaluation. This is a web page that fingerprints 30 different extensions. So you can follow the link if you're interested. Some words about related work. So there is another way to fingerprint browser extensions, another strategy via enumerating their web accessible resources. And we also compare our fingerprinting approach with those work. First of all, more than 40% of fingerprintable extensions that we found with XHound, they do not use web accessible resources at all. Secondly, XHound can still fingerprint newer Firefox extensions that use random URLs for web accessible resources. In the paper, we also propose defenses. The very important point here is to understand that all defenses cannot be trivial. And the point here is that XHound uses the intended functionality of extensions to fingerprint them. Basically, like if you want to just like to block this functionality, you basically like getting rid of this extension and of this purpose. No easy solution is possible, and what we propose in the paper is, first of all, we can try to implement some mechanism to encapsulate these visible side effects in the similar fashion as Shadow DOM does. Or we can provide some kind of namespace pollution, basically like trying to deceive the fingerprinter by introducing side effects of random samples of extensions from the XHound's output. So basically, we can use XHound for countermeasures as well. To summarize, we showed that a large fraction of popular browser extensions in the market are fingerprintable. They tend to introduce unique modifications, and they can be uniquely identified and found on web pages by web pages. And we demonstrated that like survey audiences tend to have also different sets of fingerprintable extensions, especially if you consider like some more technical audiences. Entropy comparison also showed that extensions can serve as a feature for fingerprinting browsers and users. Moreover, we also showed cases why exposing sensitive extensions is also privacy intrusive by itself. And finally, countermeasures will have to be cross-cutting and systematic changes to the architecture of browser extensions rather than quick patches. So thank you very much. Questions are welcome. There is a link to the demo again, and I'm always happy to answer the questions by email as well. Thank you.
Let's thank the speaker. Questions? So I have a question. The namespace collusion, or namespace pollution countermeasure seemed particularly promising. In the paper, you mentioned a few challenges to actually implementing that in practice. Could you comment a little more on what some of those challenges would be?
Yeah, the only challenge I can came up with is basically you need to continuously crawl the extensions present in the markets, right? And basically update your database of side effects that exist out there. But like if you can keep updating these databases, it's pretty straightforward, right? You need like to just like inject, using this database, inject like modifications to web pages.
Cool. No questions?
Hello, I'm Juarez from the P11. Thank you for the nice work.
Thank you. It's an excellent question, actually. We didn't run like a study like whether fingerprinting is already happening, but I suspect that like at least like case for particular extensions, like to find whether user uses particular extension already happening there. And of course, like there is like example with ad blockers, right? So web page already detects ad blocking activity, right? Thanks.
All right, let's thank the speaker again.